Welcome, thank you so much. We can start. So I'm going to talk today about a book that I wrote recently called Black Holes Survival Guide. It's a tiny little thing. Do you know the Mark Twain quote, "I didn't have time to write you a short letter, so I wrote you a long one instead"? Well, I spent an extra year on this project making it really short. It was a very interesting experiment. The book also features 23 original paintings by the artist Leah Halloran, who is very interested in science, and this is Leah's heavily tattooed arm holding the book that she helped make. So now you can see for scale. That's the hardcover, too, so it's really quite small. This was a real labor of love. I've been pretty obsessed with black holes for a long time, and it was interesting when I wanted to write this, I wanted it to feel like a kind of poetic but visceral journey through these concepts. I want to shuck away some of the misconceptions of black holes, that they're these monsters of mayhem and destruction, but I also want to tell you some aspects about black holes that I think you've probably never heard before. So it's kind of a combination of removing some of the stereotypes, but planting the newer ideas about black holes. And it's not meant to be a pedagogical book. It's meant to be experiential. It does have good advice should you visit a black hole, so I recommend you read it. Spoiler alert, as I signed in someone's book this afternoon, there is no escaping black holes. There's no surviving black holes. So the book doesn't end well, but it's a fun journey. I want to begin with this digital atlas. I'm going to try to distinguish when I'm showing you a painting that Leah made or I'm showing a cartoon versus a mathematical model. And this is a digital atlas, which means that every single object that's represented here, this is an image of our Milky Way galaxy, was measured and placed as accurately as possible as we could understand in that atlas. Now, we've never been able to get out of the Milky Way. We've only gone as far as the moon. This is our view of the Milky Way. This is why it's called the Milky Way, because of all this gas and dust that absorbs all this light, and it makes this beautiful milky rift between us and the rest of the galaxy. We're in the galaxy, so we're seeing it edge on. It is astounding that since Galileo, it was very recently just the anniversary of the Inquisition, in which he was placed under house arrest on June 22nd. Since Galileo, everything, very nearly everything we have ever known about the universe has come to us through light, through things that we see with light. Even if we build telescopes, because our eyes aren't good detectors of light, the telescopes are still collecting light. And yet, everything anyone has ever seen or ever will see makes up less than 5% of what's out there in the universe. And the fact that we know that is just astounding. We are a little bit of ashy residue left over from the Big Bang. We are a very tiny percentage of what's out there. Most of what's out there is in dark forms, and we don't know what they are, so we give them proxy names like dark matter, dark energy. But we really don't know what those things are. My favorite part of the dark sector is something we do know, and that's the phenomena of black holes. So I'm going to talk to you about things that are technically cannot directly be seen with light. This is also an actual observation from the Sloan Digital Sky Survey. Every object you're seeing in this actual observation of the sky is itself an entire galaxy. So our galaxy has something like 300 billion stars. Maybe 1% of them are heavy enough that one day they'll become black holes, and we'll talk about that. That means 1 billion black holes in our galaxy is not unreasonable, and you are now looking at hundreds of billions of galaxies. So each galaxy, we also believe, has a supermassive black hole at its center. So black holes are populous, right? They exist in abundance out there, and we can't see them in any of these observations. There are essentially as many galaxies in the observable universe as there are stars in the Milky Way, which is really, really astounding. And you have to think that when Einstein was working, 1905, 1916, he did not know there were other galaxies out there. It was still debated. It really wasn't until Hubble, which is in the 20s, that we had the first confident realization that the Milky Way was not the only galaxy out there. And the universe just keeps getting bigger, right? It just keeps getting bigger. This is a mathematical model. It's a very detailed mathematical model. It's not a cartoon by the physicist Andrew Hamilton of what a black hole would look like. Let's just start with the black hole, and we'll figure out how to go from there. So originally, Einstein, when he first writes down his general theory of relativity, a theory of curved space-time, where he has all of these wild ideas about what gravity and space-time in the universe are, he gets a letter from the Russian front. It's during World War I, from one of his friends, Karl Schwarzschild, who had enlisted as an infantry soldier despite being an accomplished astronomer. And between calculating ballistic trajectories in the trenches, he's reading the proceedings of the Prussian Academy of Sciences, as you do. And I can't even get my graduate students to show up on time. But here he is, and he's in the trenches, and he writes Einstein, and he says, "The war has treated me kindly enough, and with something absurdly optimistic, that I have had the pleasure to wander through the land of your ideas." And it's really Schwarzschild who first discovers the black hole. It doesn't give it that name. The name doesn't come for another 50 years. But what he does is he says, pretend to his friend Einstein that I've crushed all the matter of a star to a point. He doesn't ask how this is possible or if this would ever happen in reality. He just says, pretend. And then he begins to mathematically understand what goes on around such a fantastical object. And this mathematical model is a really nice demonstration. What happens, even though the mass is concentrated to a point, the space-time is so deformed that not even light can escape if it veers too close. It's literally casting a shadow. So what you're looking at in this simulation, are you guys not seeing any of my slides? Oh, they're going back and forth? Okay, sorry guys, you can cut this out of the video. I've got a monitor, so I don't know what's going on. So what you're really seeing is the shadow cast by light veering too close, so close that it spills down the throat of the spacetime. You can almost think of spacetime as like a waterfall that's spilling in, and even light gets dragged in. And so it's literally as though you need some source of light to cast the shadow. In that sense, it's like the shadow of a tree. Okay? What you're seeing isn't the tree. You're seeing the light that's casting the shadow of the tree. In this simulation, the Earth is falsely illuminated and it's placed really close. But another thing I want you to notice is you can never hide the Earth behind the black hole, because even the light that's literally directly behind the black hole is kind of fanning around and coming towards you unless it falls in. So what you're seeing is the Earth is behind the black hole and you can see it. So if you're in some kind of space battle, do not try to hide behind a black hole. They can see you. They can see you. So our sun will not become a black hole. It's actually not heavy enough. Einstein is very impressed by this paper. His friend has written to him. He thinks it's beautiful, but he feels nature will protect us from their formation. He doesn't think they'll actually form, but he helps him get this paper published. Fortunately, Schwarzschild dies within 6 months of the publication from an infection contracted on the Russian front, and never really lives to understand how impactful his ideas are. But they think this is just math. This is just playing. This is just pretend. You've probably seen, this is one of Leah's paintings, space-time kind of representation like this, where things are falling down the throat. What I really want you to do is think about a black hole like this. Okay? If you're exploring around a black hole and there's no source of light, this is a very technically accurate mathematical model of what you would see. You would see nothing. Black holes are completely dark. They're the darkest phenomenon conceivable. They're dark against a dark sky. If you want to see a black hole, you have to shine light around it. Or you have to let it get hazardously close to something else. Here is a painting, which I'm going to show you is not too dissimilar from the observations that we've actually seen recently, where there's hot material around the black hole. And so what we're seeing is the hot material and the shadow that's cast by the bright light. Now, this goes on for decades, that people are arguing about whether or not black holes are real, whether or not they exist. Oppenheimer's probably his most, Robert Oppenheimer was very famous for the Manhattan Project. I believe they're actually doing an Oppenheimer movie, I hope so. He's an absolutely fascinating character who's very involved with understanding the nuclear physics to build a bomb during World War II. Begins to think about nuclear physics and writes a paper, and it coincides with the day that the Nazis invade Poland on the Russian front. And so this paper basically says that he thinks nature has found a way to make black holes, but it doesn't get a lot of attention, not surprisingly. It's 1939. And the way that he thinks of for nature to make a few black holes is by killing off really heavy stars. What he's come to understand is that in the cores of stars, there are thermonuclear explosions, not at all unlike the kind of nuclear physics that was at work in the bombs. And when those thermonuclear explosions are happening, stars are bright. And that's why we have this warmth of our own sun, because our sun is regularly processing nuclear material. But eventually, they run out of fuel. And when they do, if the star is heavy enough, it will begin to collapse under its own weight. Now, it's perfectly reasonable to think the way Einstein did, which is, well, look, I can't crush a can very easily. So probably when it starts to collapse under its own weight, there are going to be these very powerful forces that just will resist what they kept calling catastrophic gravitational collapse. They kept saying these long sentences, catastrophic gravitational collapse. Oppenheimer was the first who actually started to calculate if the nuclear centers of very heavy stars could resist catastrophic gravitational collapse, and he concluded they could not. And the debate continued to go on until the 60s and 70s. But we now understand that very heavy stars can't resist collapse. It's actually astounding to think about it. Now, when the star collapses, it gets smaller and smaller and denser. Eventually, it's so dense that not even light can escape. The event horizon forms, which is what we call the shadow. The shadow is the event horizon. And when the event horizon forms, that star can no more sit there than it can race outward at the speed of light. The star is forced to continue to collapse. So it leaves the event horizon behind. It's like an archaeological record that the star was once there. And what it leaves behind is nothing. It's emptiness. The star is gone. So the star continues to collapse. What happens to it, we don't know. We can talk about what happens and our theories about what happens to the star. We've got a lot of ideas about that. But what it leaves behind, what we really mean by the black hole, is the event horizon. So I want you to stop thinking of black holes as dense objects, because really they're more like places, and they're empty, and there's nothing there. So black holes are like a place more than they're like a thing. Now, this is another mathematical model from Andrew Hamilton. It's an excellent model of what would happen if you did not pay attention in astrophysics class, and you go out into space, and you see this thing, and you're like, hey, what's that? You know? And you get too close to it. This is what you would see, because what you're seeing is the light swirling around from your own orbit. But right now, in this simulation, the astronaut has crossed the event horizon. It's empty space. It's no more dramatic than stepping into the shadow of a tree. And they, once they cross, are in terrible trouble, right? Because nothing can travel faster than the speed of light, and you have to travel faster than the speed of light to escape. So that astronaut eventually plummets and faces a very unhappy ending in the interior of the black hole. Again, we don't know exactly what fate befalls them, but we suspect it's very likely that the gravitational forces are so strong that they're ripped apart into their fundamental particles. And those fundamental particles, maybe they blow out into a new Big Bang. This is a very weird fact I'm about to tell you. Black holes are bigger on the inside than they are on the outside. It's like Doctor Who's TARDIS, right? I could hide an entire universe inside a black hole. And black holes are small. So we'll talk about how small they are in a second. They're heavy, but they're small for their heft. So something bad definitely happens to this astronaut, but my first advice is fall into a really big black hole. Surprisingly, you'll extend your lifetime longer the bigger the black hole you fall into, and the less dramatic your initial plummet will be, and you'll have some time to experience some pretty profound existential dread before you have this catastrophic moment. So there's also this phenomenon. Black holes are dark on the outside, of course, because nothing can escape, not even light, not even the star that formed it, not the person who went in and explored, but they can be bright on the inside. because all the light from the galaxy can fall in behind you, and it becomes so concentrated that you can see eons evolve, millennia come and go. You can find out what happened to the climate crisis on Earth, right? And it's all going to happen really fast for you, even though millennia can be passing or billions of years can be passing out in the universe compared to you. But that means that the light can catch up to you. And actually, at the end of whatever happens to you on the inside, the light will become so concentrated, and you know when you bring all the colors of light together that they become white, it becomes white light. So you will see this huge, bright flash of white light if you're still consistent, I don't know, when I'm hanging together enough to see it. And I call it like one of those near-death experiences where you see the light at the end of the tunnel, but it's a total death experience. So black holes are nothing, they're empty, they're a place, not a thing. They can be bigger on the inside than they are on the outside, and they can be bright on the inside. I want to emphasize that black holes are small. So this is also one of the sort of, monster black holes, and they're so big, and they're weapons of mayhem and destruction, and there's some truth to that. But they are actually tiny. If a typical black hole, 10 times the mass of the sun that comes from a dead star, it's 60 kilometers across. Okay, city-sized. The sun is 1.5 million kilometers across. It's city-sized. And you can get really close to a black hole and you're just fine. Just stay outside that horizon. You're actually okay. You can set up a very safe orbit around a black hole, put your feet up, build yourself a space station, and just watch things happen. And you could live there indefinitely. You can't get 60 kilometers to the sun, right, without it being pretty incendiary. So black holes, in a way, are more benign. Leave them alone, and they leave you alone. Black holes also come in the supermassive variety, which I mentioned if you were at the opening session today. Supermassive black holes are an absolute mystery. We don't know where they come from. So we know that there are black holes that are 10 times the mass of the sun, a couple 100 times the mass of the sun. But these are enormous. They're millions of times the mass of the sun. Some are billions of times the mass of the sun. And again, they're tiny for their heft. So you can really scale up. A black hole 1 billion times the mass of the sun is still fitting in our solar system. So it's really, really small. It's much, much smaller than billions of times across. So they're actually incredibly hard to see. And I think it surprises people to find out that we really had never seen a black hole before 2019. Okay? What we have seen are things like this. This is an astronomical observation. It is a galaxy with a supermassive black hole at its center. And when we look at it in certain light, it looks kind of quiet, like nothing's going on. When we look at it in radio light, the word radio just means that's the frequency of light that they used to encode radio signals on. It has nothing to do with sound. It's actually light. It's just very long wavelength light. Our eyes are not good detectors of radio light, but it's light all the same. We see these enormous jets. This is real observation. Those jets are 1 million light years across. It would take light 1 million years to go from one side to the other side. And what they're seeing is they know that the black hole is doing something very active on the inside. That means it's probably spinning. There's a lot of electromagnetism. Stuff's falling on top of it. If stuff's spilling in, it's getting bright, it's getting hot. The black hole's not ejecting anything from the inside outside. It's just churning up the mess around it. And so we have indirectly known that there were black holes for a long time, and we've seen black holes for a long time indirectly. But that's not the same as looking at a black hole, right? That black hole that's inside there is teeny, teeny, tiny, and what we're seeing are the enormous jets. These are real observations, again, about black holes. The Nobel Prize was awarded to Andrea Ghez and Reinhard Genzel, and also Roger Penrose, but it was Andrea and Reinhard who did these observations. What they were doing is, this is our own Milky Way again. We're going into the center of the Milky Way, so they're just way here on Earth collecting light, and they're looking at stars orbiting the center of our Milky Way. And they're watching those stars for 15 years, 17 years, 25 years, until they start to make full orbits. And what they see is they see stars orbiting nothing. Okay? They see something very heavy. They're deducing from the paths of the stars that object is 4 million times the mass of the sun, but it's less than 20 times the width. Okay? It's very tiny in that sense. And they deduce indirectly that there's a black hole. Now, deservedly, Nobel Prizes. This has been the century for black hole discoveries, by the way. It's a crazy thing. So people think Schwarzschild's idea is brilliant but not true. Oppenheimer starts to think, well, maybe black holes are real. There was this Professor John Wheeler, who was the granddaddy of all the American relativists, Richard Feynman and Kip Thorne, who now has a Nobel Prize, and all of these people, and he trained all these people. He thought Feynman was wrong. He gave Oppenheimer a really terrible time. They had a huge rift. And then in 1967, Wheeler, who has also been working on the bomb, and after that the hydrogen bomb, and after that thinking about nuclear physics, realizes that Oppenheimer had been right all along. And in 1967, after being exhausted of saying catastrophic gravitational collapse in a lecture, somebody shouts from the back of the hall, "How about black hole?" And apparently, Wheeler just foisted it on the rest of us. He has a line where he says, "The Cheshire cat fades from view and leaves behind only its grin, and the star leaves behind only its gravitational attraction." I kind of butchered that quote, but he calls it a black hole. And ever since then, it was in the lexicon, 1967. Okay? So this is 50 years after they were first proposed. It was resisted by the French. Any Francophone? It's apparently a very filthy sounding in French. Black hole, trou noir. So I don't think they don't like it very much. So we now know that there's a black hole out there, and we want to actually see it literally with our eyes. We've never seen a black hole directly. Then came this announcement in 2019, after years and years of work. Very, very partial to this experiment, this observation. I'm a very theoretical astrophysicist. I work with math on, pen on paper. I don't build things or go out and make observations. So a lot of this is, I just have so much admiration for the accomplishments of the observers. In this particular case, the principal investigator on the project was my roommate at MIT in graduate school. And loved the guy. So I knew this was coming. He wouldn't even tell me. I'm not in the project, but I knew it was coming. He's like, "Janna, I really think you should come to DC for the press announcement." So, and he has been working on it since we were in graduate school. I remember him talking about this. So this is what happens when I go to DC. I go to the National Press Club, and there's all this excitement. We all know what's coming. That black hole at the center of our galaxy, it's called Sagittarius A star, because it's in the direction of the constellation Sagittarius from where we're standing. It's 26,000 light years away in the center of our Milky Way. It's 400 million times the mass of the sun. All these things I've already said. And I'm thinking he's going to declare that they've seen Sagittarius A star. The only surprise was that they actually saw a different black hole. Now, they knew there was another candidate. The other candidate, I'll let this run. This is from the team, from the European team. It was made by the European team, but the team is absolutely international and global. There is a galaxy called M87. The M stands for Messier. Messier made a catalog of objects to avoid because they were not very interesting. And M87 was one of them. It was the 87th entry in the Messier catalog, and it was just a smudge on the sky, and he didn't know they were galaxies. He just thought, don't even bother your time with this. We now know that M87 is a satellite galaxy. It's 55 million light years away. So we're seeing it as it was 55 million years ago. Inside that galaxy, there is a supermassive black hole that is 6.5 billion times the mass of the sun. It's absolutely colossal. Yet, again, it's solar system sized, so it's spatially small for its heft. And after years of working with a coordinated system, so even though it's so heavy, it's so big, it's so far away that it is, from our perspective, trying to resolve something the size of a piece of fruit on the moon, or as my friend Shepard Dolaman, who made the announcement, said, it's like reading the date on a quarter in San Francisco from New York City. Okay? And to get that kind of resolution, they had to coordinate telescopes all over the globe. They used existing telescopes. And they used some defunct observatories. And they brought them online and they coordinated them. So as it's observing and the Earth is spinning, they link it all up and they time it all up together so that it seems as though they've taken it a snapshot with one eye the size of the Earth. So it took a telescope technically the size of the Earth. And this is the image that they returned. And you can see that what you're really seeing is bright stuff around it, and it's casting the shadow. And I want to emphasize, I'm not 100% sure what our angle is on this. I know they have estimates and measurements. But some of that light that looks like this donut-y shape, that looks like it's above and below and to the sides, some of that is coming from behind the black hole. And it's just the way the light bends at us that gives the illusion. And it's the only reason we can see the shadow, is because that happens. Otherwise, we would never be able to see the shadow. So this was the first image of a black hole human beings have ever seen. Maybe some other civilizations taken pictures of them. This was the first one we've ever seen. Then, just last month, in May, Event Horizon Telescope announced, and again, I went to Harvard to go to the post-announcement conference, and because we all knew what was coming. This time, they had seen our black hole, the one in the center of the Milky Way, Sagittarius A star. It was harder because the data was harder to deal with. The black hole is changing more rapidly. It's harder to coordinate all the observations, make it feel like one big snapshot. But here it comes, Sagittarius A star. And again, we're seeing it as it was 26,000 years ago. And here we're zooming past those stars that Andrea Ghez and Reinhard Genzel observed, and we're going deeper, deeper, smaller, smaller, tiny, tiny little thing, less than 20 times the width of the sun at 26,000 light years away. And there she is. So that's pretty exciting. Somebody said, well, what are you getting out of this? I'm just not bored yet. Okay? I'm not bored of looking at black holes yet. We have to also understand that a lot of what we're doing is just getting started on the cusp of what we can do. And there is something incredibly special about understanding that 5 billion people, something like that, looked at this black hole together. It can't be 5, it must be 1. 1 billion people. My estimates are off. I'm a theorist, and 1, 5, something like that. So 1 billion people around the globe look together at this black hole. And there's that moment, that cusp, where we're acting as a species together. And there's something so beautiful about that. I think that was the strongest feeling I had when I was at the National Press Club. I knew what it was going to look like. We knew the numbers kind of already. It was still very thrilling. I'm not minimizing it. But that was the overwhelming feeling I had, was that I knew people were looking at it all over the globe together. And that it took a collaboration across the globe to work together to make a telescope the size of the Earth. And there's something about that we really do need to learn from. If we took a fraction of that devotion, we would solve so many of these problems that we've created for ourselves. This actually precedes the black hole observation. I want to talk about this a little bit too. This also was awarded a Nobel Prize. The Nobel Prize for this, I believe, was in 2017. And let me tell you what we're looking at here. We're looking at 2 black holes that are completely, completely dark. There's no light around them. This is a cartoon from my NOVA show. This is not a mathematical model. The idea is that if you have 2 black holes that maybe were stars together, had a long life, they both collapsed, they both formed black holes, died as black holes, they're orbiting each other and they're slowly spiraling together. And in the final, final, final stages of their life together, they're like banging on space-time like mallets on a drum. Literally, the shape of space begins to ring. If you were floating nearby, it is not impossible that your ear mechanism would be ignited by the squeezing and stretching, and that you would literally hear something even in empty space. We call those gravitational waves, and we say it's very analogous to sound. Complete darkness, no light. This experiment called LIGO was the ambition of the creators for over 50 years. Ray Weiss, who got the Nobel Prize, Kip Thorne, who got the Nobel Prize for this work, were working on this when they were young men in their late 30s and 40s, and it was 50 years ago. Literally, when I was following the project before it succeeded, they said to me, we're just trying to stay alive. And you know, Ray was 85 when a lot of this stuff was happening, and is working on this experiment solidly. It's still out there. He's still on site and doing. I won't go into too much detail about the experiment, but I'll tell you what it was trying to do. It was trying to record the sound of the ringing of space. Giant detectors, they're 4 kilometers long. Again, it's not picking up light. I think of it kind of like a musical instrument. It's like picking up the ringing of the drum, and then it plays it back to us as sound. They literally sit in the control room and listen to the instrument. It cost billions of dollars, and it took 50 years, and the first generation of experiments heard nothing. Crickets. Crickets, right? A lot of scientists, including astronomers, wanted this to be over. They thought this is ridiculous and this project should be grounded. 2015 comes along, they've built the second generation of instruments. So now they're on the second generation of instruments. They've been working on it since the 50s and 60s. And 70s. And so they build these incredible instruments, and they're worried that the instrument isn't quite ready, the advanced machines. It's like August. They're supposed to do a science run in September. And they decide to keep messing with the instrument. They postpone the science run. The experimentalists are out there. Imagine this huge 4-kilometer-long instruments, one in Louisiana, one in Washington State. And eventually, in the middle of the night, they're exhausted. They put their tools down. They go home. And mercifully left the machine locked in detection mode, as opposed to offline. In the span of an hour, a signal that had been coming to us for 1.5 billion years washes over Louisiana, is beautifully recorded by the instrument. It scoots at the speed of light, even though it's not light, it travels at the same speed, washes over the machine in Washington, is recorded. Ray Weiss, he's been working on this, basically his whole life, scientific life, wakes up in the middle, 8:30 in the morning. He was sent home by his wife too, He wakes up and he says, what the hell is this? In the logs. They spend the next several months analyzing the data, and this is what they detected. This is a very sophisticated numerical simulation. It's not a cartoon. They detected the merger of 2 black holes. They're each about 30 times the mass of the sun. That makes them about 60 kilometers across each, roughly. They are in the final millisecond of their life together. It is drastically slowed down so that we can see it. They're traveling very near the speed of light, maybe 70% the speed of light. So they're orbiting incredibly quickly, and space is ringing, and they collide, and then they settle down, and they go completely quiet. So we recorded in the last milliseconds of this merger, and by the time it washed over the Earth, it rang the instruments so finely that the difference was a fraction of a nucleus of an atom over the 4 kilometers, is what they recorded. Unbelievable, another example of just an unbelievable scientific commitment and achievement. So this is what they heard. Are you ready to hear what it sounded like? Brace yourselves. Okay. Let's see. I know. I know. Like you think it's going to be baritone or something? No, it's like, the other thing is the instrument is technically tuned to the human auditory range, because black holes of this size ring space-time in the human auditory frequency. It's just a coincidence. It's just that the amplitude is so low that we could never hear it unless we were right on top of hazardously on top of the black holes. So this was, happened very far away in another galaxy. No light came out of this event. No telescope will ever see this event. Yet it was the most powerful event human beings have detected since the Big Bang. More energy came out in these gravitational waves, even though it was very quiet by the time it got to us, than all the power of all the stars in the observable universe combined. It was absolutely, and this is one of the crazy things about converting gravitational energy, just incredible power in it. Since then, we've had other black hole detections. So this century's just been like boom, 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 right? Completely, unbelievably inspiring. And so I just want to close by taking another look at a deep sky survey. This is from the Hubble Space Telescope, named after the first astronomer, Edwin Hubble, to realize that there are other galaxies out there at all. And the Hubble Space Telescope can just stare at a part of the sky. And it looked at the darkest part of the sky it could find, and it's just a tiny, about the size of a tiny piece of the moon, a tenth of the moon, like tiny little patch of the sky, and it just stares at it and stares at it. And all of these are real galaxies that it sees, if it waits long enough. There's something like 20,000 galaxies in this tiny, tiny patch of the sky, and that's how we get the estimate that there are as many galaxies in the observable universe as there are stars. We believe that every one of those has a supermassive black hole at its center. Every one has smaller black holes formed by dead stars that collide and ring space-time. And we now understand that we're in orbit around a black hole. We are in orbit around Sagittarius A star, which is what we call that black hole. We're orbiting it very slowly, and we're also falling into it. We're falling into it very slowly. It's nothing to worry about. Don't worry. Our star will definitely blow up before then. But that's our future. That's where we're going to end up. We believe that those supermassive black holes sculpted galaxies and allowed there to be regions where life forms. And we believe that one day everything that can will fall into black holes. And that is ultimately going to be our fate. So they are our past and our future, and they are no longer this anathema. They are exotic. They are spectacular, but they simply are a part of the universe that we live in. Thank you so much. Oh, I forgot to say, I'm supposed to do a Q&A. Yeah, this is the most fun part. So basically, people are going to run around with mics. If you have your hand up, somebody's going to give you a mic and ask a question, and just keep those mics cruising. Yes, if you have a mic, your floor is yours.
So I wanted to follow up on your comment. You've taken us right to the edge of science fiction. And earlier on, you made the comment that as black holes collapse on each other, eventually there could be another Big Bang. Is there theoretical support for that?
It's no longer that. I'll be honest, it's not really the most popular idea. Here's where the thinking was. The thinking was, there's probably a singularity, meaning a region of infinite curvature, where the curvature is so extreme that Einstein's theory is no longer making sensible predictions. It's kind of signaling to us that there's probably a quantum gravity theory that should take over. So we don't claim to know. But some people think, well, you know, the Big Bang was also like a singularity. Maybe I can sew them together. Not like predictive. It's not saying, I know that this happens. It's saying, could the spacetimes be sewn together logically? And they can. It doesn't violate anything to do that. So the idea that the black hole creates a singularity, which is its own Big Bang, and there's an entire universe on the inside. It's not really on the inside anymore. I don't even know how to think about it exactly. Now, it's not that popular because people think it violates entropy laws, which would be a long story to go into. But that it would, if it was true, then the universe would be very unstable to making more Big Bangs all the time, and it would be very unstable. So, but it doesn't mean that we understand it. You know, there are a lot of models which try to do quantum gravity, meaning the microscopic forces that guide matter sewn on to the forces that guide gravity sewn to. We don't know that model yet. We don't have a theory of gravity, quantum gravity. So we test things out, and some of them do look like they go into Big Bangs. I mean, it's unresolved. Yes. Oh, you don't have a mic. Oh, sorry, somebody's got the mic. Yeah. They want to make sure you have a mic. So do you mind holding? They'll get you one. Yes.
I was wondering if you could talk to the sort of information paradox in Hawking radiation.
Yeah.
And how
You want to talk about that?
I'd love to. I watched a video on it, and I
Yeah.
didn't understand.
No, that's some amazing stuff. So Stephen Hawking was rightfully famous. He made a very remarkable discovery, and it threw everyone totally off kilter. So I'm prattling on about how black holes have an event horizon. Not even light can escape. They're the darkest phenomena in the universe. They never emit any light. Hawking started asking, well, what if I studied quantum mechanics right at the boundary, just around the event horizon? Not doing quantum gravity, just regular quantum mechanics. And he realized that black holes could do something really sneaky. They could essentially steal quantum energy out of the vacuum of empty space and look like they're evaporating. Now, nothing's coming from the inside to the outside still, but what they're doing is they're absorbing this quantum energy. They're actually getting smaller, and some of this quantum energy is escaping. So from far away, the black hole is and looks like it's evaporating in radiation. Now, everyone believes that that's completely correct. That's not debated. It's absolutely beautiful. I can show it in a more elementary way in a general relativity class, how it works. But it causes a real problem, because when the black hole finally evaporates completely, the event horizon's yanked up. Where did the star go? Because the stuff evaporating was not the star. And so that's the information loss paradox, because quantum mechanics says you can't lose information out of the universe. It violates everything we believe to be sacred. The whole program of predicting the future from the past or the past from the future, all of it's messed up if this is possible. And so it caused this 50-year debate that's still going on. And I think that the answers are going to be real wacky, like, not exaggerating, quantum wormholes connecting the interior to the exterior. So the thing that radiated was actually the star, even though it never came out. I mean, it's going to be wacky, okay? It's going to be wacky. But I actually think that's probably along the right track. So the black hole will evaporate. The star will escape, not by coming out the event horizon, but by being mapped by a quantum wormhole to the exterior. Yes, you have
Hi.
your mic now.
Can you talk more about the event horizon?
Yeah.
What is it? Is it gaseous? Is
It's nothing.
it matter?
It's literally empty space. So the way to think of it is, so if I believe that space-time can be warped, I can stretch it. We see this. We see galaxies expanding. There's a way of looking at a black hole where it literally looks like a waterfall of space-time, just like space-time's just falling in. It's nothing there but space-time. How do I know space-time's curved? I can tell it's curved because if I throw something, it doesn't travel in a straight line. It follows a curve. I can literally map the curves around the Earth just by throwing things and watching them. They go like that, and they go like that, and I can trace all the curves. What happens with an event horizon is that light looks like it's traveling in a straight line, but it's actually being bent a little tiny bit by the Earth. But by a black hole, the light goes like flunk down the black hole. So the event horizon is only the shadow. Literally like the shadow of a tree. There's nothing there. Nothing there at all. It's just a region light can't get to, can't come out of. So that's what we mean by it's called an event horizon because it causally separates events that can cause and affect other events. So something that's in the black hole is an event that can't affect events on the outside. That's why we call it an event horizon. Yes, you have a mic. And then I think this gentleman in the front has been waiting to ask a question.
That was a fascinating experience,
Oh,
not
good.
just a lecture. If we can survive ourselves, what is the prediction for when we're going to fall into our own, black hole and
honestly,
disappear
I
and
don't even
evaporate?
have the number, but it's so if the universe is about 14 billion years old, I always like to say the future is much longer than the past. It's a googolplex of years. It's just an absolutely enormous number. Lots of things will happen to us before then. We're going to collide with Andromeda, which is a neighboring galaxy. Our supermassive black holes are going to merge first. Our whole solar system will probably stay intact. I don't know what orbit we'll be on around that thing. So that's the one we'll actually fall into. It'll be a new one. Yes, you have a mic here.
Are black holes always at the center of galaxies, and if so, why?
Yes, it's a great question, and it was discovered much, much later. supermassive black holes. So there's two things going on in the center of galaxies. We have supermassive black holes that are always at the centers of galaxies. We think every single galaxy, basically, unless it's ejected its black hole somehow. We don't know what they're doing there or how they got there. They're not formed by stars. They might have formed in the early universe primordially. Then there are these collisions between galaxies which might have made them grow, but it doesn't really account with the history of the universe for them to grow that big. So it's a mystery. It's one of the unsolved problems that we ask. I think it probably collapsed out of primordial stuff, skipped stars altogether. And so whether the galaxy came after or with it, it's all stuff that we're figuring out. But in addition to every galaxy having a supermassive, each one probably has billions of just regular black holes. And in the center, we know that there are little black holes orbiting the supermassive. So little ones falling in to the big one. Whoever has a mic can ask. And let me just check the time, because how are we doing with time, Katie? I don't know where my clock is. 10 minutes. OK.
So
yes.
I've got two related questions. One is, you alluded to it with Hawking. Is there a theoretical limit to how small a black hole can be?
It's great,
and
yeah.
secondly, are there black holes that aren't associated with galaxies floating around that we can't even detect?
Probably every once in a while a black hole gets ejected out of its galaxy. But stars do that too. Occasionally we have errant stars wandering around the universe outside of their galaxies. So that just like, sometimes there's like a near, you know how sometimes we use Jupiter as a slingshot to go, sometimes the black holes just near miss each other and they throw each other out of the galaxy or something like that. But no, we can't really see them. No, it's hopeless to see those. Sometimes we look for something called microlensing, where if a black hole passes, it makes a star twinkle. Try to guess, but it's pretty hard to do. So there's never been a confirmed observation of that. What was the other part of your question? How small? Oh, that's a great part of the question. Black holes are amazing because, I didn't say this, I think that they're fundamental particles, kind of like how an electron is a fundamental particle, or like in particle physics. They're fundamental in the following sense. Black holes are completely featureless. So if I make a black hole of a certain mass, maybe it's spinning like the Earth, maybe it has some electric charge. That black hole is indistinguishable. It is absolutely identical to every other black hole with those three numbers. And that makes them like fundamental particles. I don't mean one has a little bump on it. They are intolerant of any deformation. They are featureless. If you try to put a bump on it, it shakes it off in these ringing of the space-time gravitational waves, and it settles down, and it becomes like a gigantic, astronomically large fundamental particle. The size of them, they can be any size at all. So the smallest, we know theoretically, is probably weighs about as much as a pile of sand, or sesame seeds maybe, a little pile of sesame seeds, but would be much, 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 much smaller than a nuclear particle spatially. And those are, it's conceivable, are made in the early universe. And they probably explode through Hawking evaporation, and they're no longer around. But that's the only cutoff I know of. They can be as big as the universe will accommodate, and anything in between. It's just a matter of how to make them. I'm a little conscious of time. Let's take one more question, so whoever has a mic, I guess. Yes?
How do supermassive black holes affect how galaxies develop, or the fate of those galaxies?
Yeah, so we used to think, even if a black hole is 4 million times the mass of the sun, that's not a lot of mass compared to all the stars. They weigh much, much more in the galaxy. So mass-wise, it doesn't seem like it was that important. So it was kind of thought, oh, maybe they just happened to be there. But now I think we absolutely understand that they sculpted the galaxies. So if you look at those big jets, there was a period in our past when our black hole was a quasar, which is an incredibly energetic engine with huge jets coming out. And probably what was going on then, it was blowing out a lot of like gas and material, and it modulated the galaxy to be a certain size, and it also created regions where planets could form and things like that. So we think black holes might have been incredibly fundamental in how galaxies look. Even though they're just kind of just sitting there now. So if you're a distant galaxy very far from ours, so you're seeing us as we were 1 billion years ago, or maybe a couple billion years ago, our black hole probably looks like a quasar, because you're seeing our black hole as it was in the past. and now our black hole's quiet. Does somebody have a mic? I'll give one last question to the person who has the mic. Okay, here.
How do you know that the universe was empty before the Big Bang?
Well, I don't. There's two different ideas. One is that there was no universe before the Big Bang. That was the original. The Big Bang is the moment time begins and space begins. And before that, there was no universe. I don't know that. It's just one of the ideas. Another idea, which is a little bit different and maybe a little more modern, is that there was a crazy space-time. It was very lumpy. It had very irregular, and a little tiny piece of it, like the tiniest little patch, in some sense caught fire. Like it just got trapped in a really high energy state. That blew up, and that's our Big Bang. Now, because space-time is confusing, what one person thinks is space, another thinks is time, when we're looking back, we can't see the other, we see that as time. Okay, so that's our past. So there's no us looking at the other bubbly regions. I don't know. I guess I'm done. I guess it was an hour. I just think it's good. We're good. Do you mind putting on the slide, the last broadcast slide? Thank you so much. I ruined my applause moment. It was very nice. Can we maybe put on the broadcast slide? It's like the second to last slide, or third to last slide. I just want to say that this is a labor of love. I've started this magazine called Pioneer X Broadcast. I'd love it if people checked it out. It's online. It's free. Everything we do is free and nonprofit, open to everybody. And we feature a lot of really interesting scientists and artists rubbing together, and technologists and musicians, and we have a bunch of articles on black holes on that. Thank you again. Thanks so much.